Good evening and welcome one and all to the 20th and final session of research discussion on graphs and groups. Here we have our lead speaker, Professor Peter J. Cameron, uh, to just conclude or to inform all of you about the progress resulting from RDGG. May I request Professor Cameron to start with his presentation.
Fine, thank you very much. Okay, so I'm going to talk about some mathematical developments that have happened because of the research discussion. This is not everything that has happened, as I will say. There are still some things that are going on that we're thinking about, and there will certainly be more. But I want to talk about 5 particular topics that I have been involved with, and this picture, which of course is a picture of the mountainous part of Kerala, is supposed to indicate that this is beautiful country that we're exploring and that we can go on exploring it. Anyway, I want to begin by thanking the organization of the research discussion, especially Vijay and Aparna. At a certain point, I asked Vijay about why he'd set this up, and he told me that he'd acted according to the words of Krishna in the Bhagavad Gita. To action alone one has the right, but not to its fruits. So he saw my paper on the archive and he acted. And now we're all enjoying the fruits of his action. So I'm very grateful for that. And I've been working with a number of people. Here are some of them. This is not a complete list. These are some of the people who have taken part in the seminar and whom I have been discussing things with. And some of this work is what I'm going to be talking about in this talk. So, as I say, I want to summarize some of the progress on 5 particular topics, but there will be more. So this is not the end. It's the end of the series, but it's not the end of the research. So here are the topics that I want to talk about. First of all, when is the power graph of a group a cograph? This is a topic that I raised in my original talk that we've made some progress on. The Clique number of the power graph. This was something that was already known, but if you look at it again, you can get some new insights, which I want to tell you about. The matching number of the power graph. So you see, it's mostly about the power graph, but I will say a little bit about other things. Now, I started off the lectures giving you a hierarchy of graphs defined on a group. So this is just a one-dimensional hierarchy, each graph contained in the next. But we've now got an extension of this to a 2-dimensional hierarchy, and I want to say a little bit about that. And finally, a question that came up very early on in the series: are zero divisor graphs of local rings? Right, so as I said, this is not a complete account of everything that's come out of the research discussion. There will be more, but I will just talk about these 5 topics. That's all that time will permit, I think. Anyway, so let's go. Briefly to remind you about the hierarchy, and as I said, we'll mostly be discussing the power graph. So you start off with a finite group G, and the rule for joining 2 vertices in the power graph is that one of X and Y should be a power of the other. Then there's the enhanced power graph, where you join X to Y if the group that they generate is a cyclic group, or another way of saying that is that there's some other element Z such that both X and Y are powers of Z. The deep commuting graph, which says that if you take any central extension of G and you join X and Y if they're inverse images in that central extension commute. I won't say anything about that one, it's the most complicated. The commuting graph, you just join them if they commute. In other words, if the group they generate is abelian. And the non-generating graph, where we join 2 elements if they don't generate the whole group. So the first 4 always form a hierarchy. And the last one sits at the top, provided either G is non-abelian or G is not 2-generated. So except for 2-generated abelian groups, these 5 types of graph form a hierarchy for a given group. And most of the talk will be about the power graph, but some of the others will come in from time to time. So that's our basic setup. So the first question I promised to talk about is, when is the power graph of G a cograph? So just to recall, a cograph is a graph that has no induced subgraph isomorphic to the 4-vertex path. And cographs have a very, very tight structure. They can be built up from the trivial graph by the operations of disjoint, union, and complement. And let's just make a small observation here. If you look at the class of groups whose power graph is a cograph, this is the class that we're trying to determine. Well, it's subgroup closed, because if you take the power graph and you go down to a subgroup and look at the induced subgraph on that subgroup, that is exactly the power graph of the subgroup. So if the whole thing contains no 4-vertex path, then neither does the subgraph. So this class is subgroup closed. So as soon as we've excluded a group, we've excluded all of its, as soon as we've included a group, we've included all its subgroups as well. And right back at the beginning, we had already been working on this. I've been working with Pallabhai Manna and Ranjit Mehtari, and we had determined all the nilpotent groups that have this property. They are very restricted, groups of prime power order and cyclic groups whose order is the product of 2 distinct primes, and that's all. And that actually turns out to be quite a very powerful lever to attack the general problem, which we haven't finished yet, but we've made some more progress that I'd like to tell you about. So this paper has actually just appeared fairly recently in the Electronic Journal of Combinatorics. So can we get further? Well, I want to talk about or mention a problem which has been solved and which is a subproblem. This is a class of groups contained in the groups whose power graph is a cograph. These are the groups in which all elements have prime power order, so EPO groups for short. So an EPO group is a group where every element has prime power order. And if you have a group G, then the following conditions are equivalent. The first is that it's an EPO group. Well, in an EPO group, every element has prime power order, so the power graph is equal to the enhanced power graph, because 2 vertices are joined in the enhanced power graph if they generate a cyclic group. But if that cyclic group has to have prime power order, then one of those 2 elements would have to be a power of the other. The one of smaller order would be a power of the one of larger order. Then the third way of stating that is that the Grunberg-Kagel graph, or prime graph of G, has no edges. This is the graph whose vertices are the prime numbers that divide the order of G, and you join P to Q if the group contains an element of order P times Q. But in an EPO group, that's precisely saying that there are no elements of order, a product of 2 primes, so the Grunberg-Kagel graph is a null graph. Well, groups that have these properties also have the property that their power graphs are cographs. I'm not going to stop and prove that, but this says that EPO groups form a subclass of the class of groups whose power graphs are cographs. And EPO groups have quite a long history. It goes back to Graham Hickman in 1957. And by 1962, Suzuki had found all the simple EPO groups. These groups include some Suzuki groups. And about that time, Suzuki found his infinite family of simple groups, and among them were some EPO groups. So Suzuki found all the simple EPO groups in 1962. But the complete determination has only been found very recently by Natalia Maslova and me. It's on the archive. I'll give you the reference later, but it's not yet published. So this is a sub-problem of the problem of groups whose power graph is a cograph, and it is now solved. So we would like to press on to the general problem. Well, what I've done with Mana and Mehetari is found all the non-abelian finite simple groups whose power graph is a cograph, except that we haven't really found them all because there are some hard number theoretic problems which get in the way. So this is a summary of what happens. For the group PSL2Q, where Q is a prime power, if Q is a power of 2, we put L and M to be Q minus 1 and Q plus 1. Now, PSL2Q with Q a power of 2 contains elements of these orders. So, in other words, according to the theorem that I told you before, it would be if the power graph is a cograph, then each of these numbers would have to be either a prime power or a product of two distinct primes by the theorem that we proved and has just been published. If Q is an odd prime power, these cyclic groups have order just half of what they were before, Q minus 1 over 2 and Q plus 1 over 2. So the power graph is a cograph if and only if each of L and M is either a prime power or the product of two distinct primes. And it seems to be beyond the reach of number theory at the moment to decide which of the prime powers Q for which that condition holds. So next come the Suzuki groups, and for the Suzuki groups, there are cyclic subgroups of orders Q minus 1, Q plus square root of 2Q plus 1, and Q minus square root of 2Q plus 1. Now, Q, for a Suzuki group, Q has to be an odd power of 2. So this square root of 2Q looks like an irrational number, but it's not really. If Q is an odd power of 2, this is just an integer. So these three numbers are orders of cyclic subgroups, so we have the same conclusion. The power graph is a cograph if and only if each of those three numbers is either a prime power or the product of two distinct primes. Now here we have more information because we have three numbers, not just two as we had in the case of PSL2Q. So this might be a slightly easier problem, I don't know. We haven't managed to make any progress on it, but so there is a problem. Find the Q for which that is true. And apart from these, there's only one more non-abelian simple group whose power graph is a cograph, and that's the group PSL3,4. So we don't have to worry about the sporadic groups or the exceptional groups of Lie type or anything. They don't occur. So we've managed to show that what I've told you is the best description we have now of the simple groups whose power graph is a cograph. And this is essentially what I said before. These groups have cyclic subgroups of these orders. And so if their power graph is going to be a cograph, these numbers have to be either prime power or product of two distinct primes. And for the other, we simply have to go through the finite simple groups and their subgroups and show that in each case we can find an induced path of length, of an induced four-vertex path in the power graph. So that's the simple groups. Now we've now got to the stage where EPO groups were back in 1962, and it took quite a long time to finish the job off. So there may be still quite a bit of work left to do, but that's where we are with that problem at the moment. So that's our first topic. Now I want to talk about the Clique number of the power graph, the size of the largest complete subgraph. And as I told you, this problem has already been solved. So what is there to say? Well, you'll see what there is to say. Sometimes it's good to go back to a problem where you know the solution and just look at it in a slightly different way, and you might learn something new. And this is what has happened. There's a formula for the Clique number found by Alireza, Irfanian, and Abbas. And this, you can look it up in the survey paper on power graphs that has just appeared online in the AKCE journal. The references are at the end. So when we were writing that paper, it gave me the opportunity to go back and look at their proof. So their formula is a rather complicated sum that takes a couple of lines to state. So I like things to be simple if I can make them simple. So this is what happens. First of all, if you compare the power graph to the enhanced power graph, you see, has some extra edges. And so the Clique number cannot get smaller, it could only get larger. So the Clique number of the power graph is less than or equal to the Clique number of the enhanced power graph. And in the paper, this is the one that went on the archive that Vijay saw and started up this series, I showed that there's an inequality in the other direction. In other words, there's a bound for the Clique number of the enhanced power graph in terms of the Clique number of the power graph. And the function I gave in that paper was exponential, and I said this is probably not best possible. Well, now we know the best possible result. It's just a little faster than linear. It's order of n log n. So a satisfactory solution to that open problem, I think. And it just came out of looking again at what's going on here. So let me take you through it. We start with cyclic groups, and I'll explain why we start with cyclic groups in a moment. But let's look at the power graph of, well, I'll explain now why we look at cyclic groups. If you have an edge in the power graph of a group, that's a pair XY, where one of them is a power of the other. So they both lie in the cyclic group generated by one of them, right? So every edge of the power graph is contained in a cyclic subgroup. And it's a general fact about groups that if you have a set of group elements with the property that any two generate a cyclic group, then the whole set must be contained in a cyclic subgroup. So that means any clique in the power graph is contained in a cyclic subgroup. So we immediately see that the clique number of the power graph of G is simply the largest clique number of the power graph of any cyclic subgroup of G. So we only have to look at the cyclic subgroups of G, pick the one that has the largest clique number, and that will be the clique number of G. And I'll give you an example later. It's not always obvious which the right one to choose is. So the problem is to find the clique number of the power graph of a cyclic group. So we have to address that problem. So let's turn to that problem. So we define the function little f. Little f of n is the clique number of the power graph of the cyclic group of order n. So this is just a function of n, and I'm going to just think of it as a number theoretic function. If we were doing number theory and not group theory or graph theory, you would be not surprised to be told that f satisfies a nice recurrence relation, and here it is. F of 1 is equal to 1. In the cyclic group of order 1, the largest clique has size 1, that's clear. And also, if n is greater than 1, f of n is equal to Euler's function of n plus f of n over p, where p is the smallest prime divisor of n. Now, I'll tell you why this is true. I'll leave out some details of the proof, but I'll give you the overall explanation of why this is true. Well, the generators of the cyclic group are dominating vertices in the power graph. They're joined to everything. So that means any maximal clique must contain all the generators. And the number of generators of Cn is Euler's function of n. So that's where the phi of n comes from. So once you put in the generators, what else can you put in? Well, you can show that the rest of the clique must be contained in a proper subgroup. And you can also show that to get the largest clique, you should take the largest proper subgroup. And what's the largest proper subgroup of a cyclic group of order n? Well, it's the cyclic group of order n over p, where p is the smallest prime divisor of n. So that's why that recurrence relation holds. But once we've got that recurrence relation, rather than just expand everything to get a formula, let's look what we can do with it. Well, you can show from that, it's quite an easy calculation, that f of n is less than or equal to 3 times phi of n. You just have to look at what f of n over p could be. So this is a proof by induction, basically. But in fact, if you look at the ratio of f of n to phi of n, you find that the lim sup of this ratio is some strange constant, 2.648, and so on. I've written it down here to 10 places of decimals. It's very easy to calculate, as I'll show you in a moment. So that f of n is at most 2.648 times phi of n. And it's possible to say exactly which numbers n approach that bound. But there's a formula for that constant. Here it is. You let P1, P2, and so on be the primes in order. So P1 is 2, P2 is 3, and so on. Now you take the product of 1 over Pi minus 1 over the first k primes, and then you add that up over all values of k. So for k equals 0, this is the empty product, it's 1. For k equals 1, there's only one term in the product, and it's 1 over 2 minus 1, which is another 1. So that's 1 plus 1, which is 2. For k equals 2, we have 1 over 1 times 1 over 2, which is a half. So that takes you up to 2.5. And if you go on adding up terms, this is what you get. So a little problem here. This number here is the lim sup. So it's the largest limit point of the set of all these ratios. So if you look at all the ratios fn over phi n for all natural numbers n, then this is the largest limit point of that set. But what other limit points does it have? So the problem is, can we determine all the limit points of that ratio? Well, I haven't given much thought to that, but it looks like it might be a doable problem. So if you like number theory, that might be a good problem to look at. So now back to general finite groups. Remember that omega of the power graph is the maximum of f of m, where m runs over all the orders of cyclic subgroups, or to say another way, just the orders of elements of G. So if I give you the list of orders of elements of G, you can calculate omega of the power graph of G from it. And in fact, you don't need all the orders, because you can see fairly easily that if A divides B, then f of A is less than or equal to f of B, essentially because the cyclic group of order B contains a subgroup which is cyclic of order A. So it's enough to maximize over orders which are maximal with respect to divisibility. Not maximal as numbers, but maximal with respect to divisibility. So let's have an example. Just before I do, let's just observe that the maximal cliques in the enhanced power graph are just the maximal cyclic subgroups. So you maximize over the same set, but m rather than f of m. So here's the example. So we take G to be the group PGL211, and the maximal orders of elements in this group are, by divisibility, are 10, 11, and 12. The other orders are all divisors of these numbers. And if you work out from the recurrence relation, you find that f of 10 is 9, f of 12 is 9, but f of 11 is 11. So f of 11 gives you the maximum value. So the clique number of the power graph is 11. But the clique number of the enhanced power graph is just the largest of these numbers, which is 12. So you see, this comes from 12, but this one comes from the cyclic group of order 11. So it's not true that omega of the power graph is equal to f of omega of the enhanced power graph. But it's bounded by it, because so we have omega of the power graph greater than or equal to f of omega of the enhanced power graph, because this number in the brackets is the order of some cyclic subgroup of G. So it's one of the terms that you have to maximize to get omega of the power graph. And also we know that f of n is greater than or equal to phi of n, and phi of n is greater than or equal to, so you look in number theory and you find that there's a bound for this, e to the minus gamma times n over log n. Gamma is the Euler-Mascheroni constant. And if you put all that together, you see that if omega of the power graph is m, then omega of the enhanced power graph is at most cm log m. And this is the bound that I told you about before. So this is the answer to bounding the Clique number of the enhanced power graph in terms of the Clique number of the power graph. And these bounds essentially can't be improved, because this bound for phi of n is essentially best possible, and the other things are just correct up to constant ratios. So you can look in the survey paper to find an account of that. Okay, so continuing on. Oh, yeah, sorry, one more thing before I do. A finite group satisfies omega of the power graph equals omega of the enhanced power graph. What would that mean? That would mean that there's a cyclic subgroup of prime power order which gives you the maximum value. So this holds if and only if the maximum order of an element of G is a prime power. So that's a rather strange condition, but it is a necessary and sufficient condition for a group to satisfy this equality. And once you've written that down, you see, well, actually, this is a special case of a wide class of problems. If you take any two types of graphs in the hierarchy, you take any graph parameter, let's assume it's a monotonic parameter, it gets larger when you put in more edges, describe the finite groups that satisfy P of AG equals P of A primed of G. You see, that's exactly the form of this. If you take P to be Clique number, and A and A prime to be the power graph and the enhanced power graph, you have precisely an instance of this general problem. So there are many general problems that you could extract from this question, and there's the solution to one of them. And I just observed that I took you through groups in which two of the graphs in the hierarchy are equal in the first lecture. So this is a generalization saying even if the graphs are not equal, is the value of this parameter the same? Can we characterize the groups that do that? So let's press on. So I'll press on to matching number. The matching number of a graph is the largest size of a set of pairwise disjoint edges in the graph. And we had a talk about this back in June, and there's a little bit more progress since then, which I'd like to tell you about. But first of all, just let's observe, if G has odd order, the power graph of G has a matching covering all but one vertex, which is clearly the best you can do, because in a group, if you have an odd number of vertices, you can't cover them all by pairwise disjoint edges. You have to miss out one, and in the case of the power graph, you don't have to miss out more than one. You just match each element to its inverse. An element and its inverse are always joined in the power graph. So, and no element is equal to its inverse except the identity. So the identity is the only element that doesn't get matched. So from now on, I will assume that the order of the group is even. And if you're looking at matching numbers, there's always the good old alternating chain argument. You can use that to prove that if you take S to be the set of elements whose square is the identity, so this is the identity together with the involutions in the group, then you can find a maximum size in the power graph where the unmatched vertices all belong to this set S. So that's just an alternating chain argument. And so in particular, you see, if G is a group with a unique involution, then the power graph has a perfect matching, because if you take a matching in the theorem, we know that the unmatched vertices will lie in that set S, consisting of the identity and the involution. But the identity and the involution are joined. So if we hadn't got that edge in the matching, we could add it in and get a perfect matching. The converse is not true. There are other groups that have perfect matchings. Now, I wanted to spend just a little bit of time on a quick tutorial because there's a very interesting class of groups here, the groups with a unique involution. They're all known, but this is maybe not as well known as it should be. So this is a paper I wrote with Lotzi Babai back in the year 2000. The question was originally asked by Coxeter because he was interested in geometry, and he observed that the binary polyhedral groups have unique involutions, and essentially asked about other groups with this property. Well, here's a complete classification. I will go through it fairly quickly. So if G has a unique involution, then when it forms it's in the center of the group, so you can factor it out, and you get a group with cyclic or dihedral Sylow-2 subgroups. But the interesting thing is the converse. If you have a group with cyclic or dihedral Sylow-2 subgroups, then you can lift it up to a group twice as big with a unique involution, such that when you factor out that involution, you get H. So the first part, as I say, is straightforward. The Sylow-2 subgroup of G has a unique involution, so it must be a cyclic group or a generalized quaternion group. And when you take the quotient, you get a cyclic or dihedral group. The second part is a little bit more intricate. It depends. There's a beautiful cohomological argument due to George Glauberman, which Babai and I put in our paper. So all we need to do is classify the groups with cyclic or dihedral Sylow-2 subgroups, and then for each of those, there's a unique cover of that which has a unique involution. And modulo the largest normal subgroup of odd order, these must be subgroups of P gamma L 2Q containing PSL2Q for an odd prime power Q, or the alternating group A7, or a Sylow-2 subgroup of G. Those are the only possibilities, and these are Burnside's transfer theorem for cyclic groups and the Gorenstein-Walter theorem for dihedral groups. So we have the classification of those, and we know each such group has a unique lifting with just one involution. But now going back to our problem of the matching number, we have a complete answer for abelian groups. If G is a finite abelian group of even order, let I of G be the set of involutions, not including the identity, and O of G the subgroup consisting of elements of odd order. The elements of odd order in an abelian group form a subgroup. If O of G is greater than or equal to I of G, then the power graph has a perfect matching. Otherwise, we can tell you exactly how many vertices are unmatched in a matching of maximal size. It's just the size of I of G minus the size of O of G. And interestingly enough, exactly the same statements hold for the enhanced power graph. It has a perfect matching if this condition is satisfied. Otherwise, the number of unmatched vertices in a maximum matching is this. So for abelian groups, the power graph and the enhanced power graph have maximum matchings of the same size. This is not, the first statement is false for non-abelian groups. The symmetric group S3 has 3 involutions, 3 elements of odd order, so we have equality here, but a maximum matching has only 2 edges. And I simply remark here that I posed a general problem earlier. Matching number is a monotone graph parameter, and the question is, which are the groups for which the power graph and the enhanced power graph have the same matching number? We don't know any example of a group for which that's not true, and it's conceivable that this is true for all groups, but we don't know. So now let's press on. So now to this two-dimensional hierarchy. So this is the hierarchy, as I thought of it originally, is a nice playground to ask questions about graphs on groups and how they relate to one another. But now this hierarchy has grown into a second dimension. So let me say a little bit about this. So the idea of this was in Lavagna's talk earlier on, and all I've done is generalized it just a tiny little bit. So we start off with one of these types of graph defined on groups, one of the types in the hierarchy. So maybe the power graph, maybe the commuting graph, and an equivalence relation on the group, which might be conjugacy or might be having the same order. So the one that Lavagna talked about was the case where A is the power graph and B is the relation of having the same order. Now we look at the B equivalence class containing G denoted like that. So I'm going to generalize the concept that we had earlier and define the B super A graph. The B super A graph. B is the equivalence relation, A is the type of graph. So we take the vertex set to be all the elements of the group. We join G to H if the sum edge from the equivalence class of G to the equivalence class of H. And I make a convention that each equivalence class, all the vertices are joined. So I'm thinking of the graph, the A graph, as having a loop at each vertex, if you like, because in a sense they do. The rule for joining, if you don't specify no loops, it would naturally give you loops. So Lavagna talked about the superpower graph. So I will now call it the order superpower graph. So order is the equivalence relation and power graph is the graph that we're applying it to. But I will also talk about the conjugacy superpower graph. So now we have a two-dimensional hierarchy because as the type of graph moves up through the hierarchy, we get more and more edges. But as the equivalence relation becomes successively, as the equivalence classes get larger, we also get more and more edges. So we have a hierarchy in two directions. If B is the relation of equality, then the B super A graph is just the A graph, so the power graph or commuting graph or whatever. If G is abelian, then conjugacy, two elements are conjugate in an abelian group if and only if they're equal. So the conjugacy relation coincides with the equality relation, which means that the conjugacy super A graph is just the A graph. That's not true in general for non-abelian groups. But so I'm going to tell you just one thing about this hierarchy, this two-dimensional hierarchy. I thought, well, I've made some definitions. They're not much use unless I can actually prove something. So I'm going to tell you a theorem about them. So the question I'm going to answer is, take three types of graph. I'll take the power graph, the enhanced power graph, and the commuting graph, and take three equivalence relations. That will be equality, conjugacy, and same order. And ask, in which case, for which groups is the corresponding graph a complete graph? And so to save room in my table, I'm going to use this asterisk to mean G contains an element whose order is equal to the exponent of G. In other words, that says that if you look at all the orders of elements of G, they are precisely all the divisors of some number m. Right, so here's the theorem. We're going to take power graph, enhanced power graph, or commuting graph. We're going to take those graphs themselves, or the conjugacy supergraph, or the order supergraph. When is it complete? Well, this table gives you the answer. For just the ordinary power graph, it's complete if and only if the group is a cyclic P group. For the enhanced power graph, it's complete if and only if the group is cyclic of any order. And for the commuting graph, obviously, it's complete if the group is abelian. In this conjugacy row, we have exactly the same answers: cyclic P group, cyclic group, abelian group. For order, they're a bit different. We have P group there, and we have condition star in the other two cases. That's the condition that there is an element whose order is the exponent of the group. So that's the complete result about when the graph is complete. And I'm going to just prove one bit of it for you. I'm going to take the conjugacy supercommuting graph. So remember what this graph is. The vertex set is G. We join two elements, little g and little h, if some conjugate of little g commutes with some conjugate of little h. I'm going to show you that graph is complete if and only if G is abelian. Now, going back to the table, if I could prove that, so if I can prove that we have abelian in this box, then these graphs are lower in the hierarchy, so they will also, the groups will also be abelian in those cases. And as I said, for abelian groups, the conjugacy relation coincides with equality. So once I've proved that this entry is abelian, it will follow that this row coincides with this row. So what my job is just to prove that this entry is abelian. In other words, that the conjugacy supercommuting graph is complete if and only if the group is abelian. So here's the proof. In one direction, it's trivial because if the group is abelian, then any two elements commute, so this graph is obviously complete. So let's go the other way around. So suppose we take a group G. Suppose that the conjugacy supercommuting graph is complete. What does that mean? It means that if I take any two elements G and H, then there's a conjugate of G and a conjugate of H that commute with one another. But you see, if there's a conjugate of H that commutes with a conjugate of G, there will be a conjugate of H that commutes with G, because you just undo the conjugation of G. So this is a group in which for any two elements, there's a conjugate of one that commutes with the other. Now, there's an old result going back to Jordan in the 19th century that says that if you have G as a finite group, H is a proper subgroup, then there is some conjugacy class in G which is disjoint from H, some conjugacy class that's completely outside the subgroup H. So I'm going to apply that theorem, and I'm going to take H to be the centralizer of little g, the set of all the elements that commute with G. Now, if H were not G, then according to Jordan, there would be a conjugacy class, none of whose elements commute with G, because none of them lie in the centralizer of G. But that's a contradiction to our assumption, which is that for any G, there's a conjugate of H that commutes with G. So that says it's impossible that the centralizer of G is a proper subgroup, so it must be the whole of G. That means every element of the group commutes with little g, so little g belongs to the center of the group. But that's supposed to be true for all the elements of the group. So if every element lies in the center, that's exactly saying that the group is abelian. So that's the proof of that. Okay, so on to the final topic. Are zero divisor graphs universal? Now, early on in the series, there was some discussion about whether this was true. And so I'll call a class of graphs universal if every finite graph is embeddable as an induced subgraph in some graph in the class. So now the question we're asking is it true that for any finite graph, you can find a finite ring whose zero divisor graph is contains that graph as an induced subgraph? I told you back at the start that various classes of graphs, enhanced power graphs, deep commuting graphs, and generating graphs or non-generating graphs are all universal. All those types of things are universal. So for every finite graph, there is a group such that that graph is embeddable in its enhanced power graph. That's not true for power graphs, because power graphs are comparability graphs of partial orders, so they're a rather restricted class. All their induced subgraphs are also comparability graphs of partial orders, and in particular they're perfect. So power graphs are not universal, but the other types in the hierarchy are. So we had a discussion about whether zero divisor graphs of rings are universal.
Hello, sir.
Yes, yes.
Sir, zero divisor graph diameter must be less than or equal to 3, right? So how that will affect this one? Universal concept.
Sorry, say that again. The zero divisor graph, what must be less than or equal to 3?
Diameter.
The diameter.
Yeah.
Oh, that doesn't matter. That doesn't matter. All we're asking is that every graph occurs as an induced subgraph. And a graph of diameter 3 can have induced subgraphs of much larger diameter. You see, I'm not asking that the whole graph, that any graph can occur as the zero divisor graph. I'm just asking that it can occur as an induced subgraph of the zero divisor graph.
Okay, sir. Okay, sir. Yeah.
Okay.
There is a possibility. Yeah. Smaller subgraph can have bigger diameter.
Yes, it can be a quite small subgraph, and indeed in the examples it is. The ring is much larger than the graph. But anyway, so that's the question that we thought about. And indeed, for general finite commutative rings with identity, zero divisor graphs are universal. And so this is the proof that Arun Kumar came up with. We use Boolean rings. So a Boolean ring, the elements are all the subsets of a finite set, and sum is symmetric difference, product is intersection. So the zero divisors are the AB equals 0 means that A and B are non-empty sets whose intersection is 0. So all we have to do is take a graph, take its complement and represent that as the intersection graph of a family of sets. In other words, represent the complement as a graph where two vertices are joined if and only if the sets intersect. And it's not so difficult to do that. This is a quite well-known fact about intersection graphs. And so once we've done that, we have the graph embedded as an induced subgraph in the zero divisor graph. So we can do that with Boolean rings. We can do it with various other classes as well. But we turn to the question, what about local rings? Are the zero divisor graphs of local rings universal? Local ring is a ring with a unique maximal ideal. And my first thought was, no, they won't be. And I came up with this. If R is a finite local ring whose maximal ideal is principal, that means generated by a single element, then its zero divisor graph is a threshold graph. A threshold graph is a graph where you put weights on the vertices. Two vertices are joined by an edge if the sum of their weights exceeds some given threshold. Now, this is a very well-structured class of graphs. It's included in the cographs, but it's a much smaller class than the class of cographs. So for finite local rings whose maximal ideal is principal, the zero divisor graph is a threshold graph. However, Kavaskar pointed out that this is not true in general, and now we have a characterization of rings whose zero divisor graphs are threshold. But we also have the answer to the original question, and the answer is yes, local rings, zero divisor graphs of local rings are universal. Every finite graph is isomorphic to an induced subgraph of the zero divisor graph of some finite commutative local ring with identity. So that's the answer to the question about local rings. So that's a paper which is now in preparation, and we hope it will be ready to submit fairly soon. But I'm afraid I've not been working on it for a little while because I've had various other things to do. So that's essentially the end. I'd like to thank you all for being part of this research discussion group. And I'd like to end up with a little comment. I told you right at the beginning how Vijay quoted to me the words of Krishna in the Bhagavad Gita. Well, there's possibly the greatest poet in the English language in the 20th century, T.S. Eliot. One section of his poem, The Dry Salvages, is a commentary on the Bhagavad Gita. And this is his paraphrase, which I think serves us very well at the present moment. Not farewell, but fare forward, voyagers. So I want you all to fare forward in this enterprise of finding results about graphs defined on groups, share the results, and let's see just how far we can get on this, because I'm sure we can get much further than we've got so far. So with that, here is a list of references. This is the zero divisor graph paper in preparation. The others are all either on the archive or online ahead of print, or in some cases actually published. So these are the papers that I think relate, mostly new papers that relate to the topic, but I put in two older papers, the one by Alireza Irfanian and Abbas, giving the formula for the clique number of the power graph, and my paper with Lotzi Babai, where we classify the groups with unique involution. So that's the end of my talk then, and thank you all very much for being part of this research discussion. Thank you.
With that, we come to the end of RDGG. Next Wednesday at 5:30, definitely I will, and I think at least some of you will miss RDGG. Though RDGG is over, the discussions initiated, the research work going on, way down RDGG will continue, I am sure. So thank you all for cooperating, and that's it. Thank you.